Welcome to this lecture on transition metal organometallic chemistry from principles to applications. In the last few lectures, we have been discussing an important class of transition metal organometallic compounds, mainly the transition sigma alkyl complexes, and we are looking at various facets of this particular chemistry. We looked at how these compounds were synthesized, what are the reactivity, what are the stability issues with respect to the compounds, and how these issues can be resolved by understanding the mechanism by which these compounds decompose. We also looked in the last few lectures as to methods which are available in enhancing the stability of these sigma alkyl complexes. And with that in the background, we are going to discuss something very interesting in today's lecture, which are the applications of these transition metal sigma alkyl complexes. To begin with, I am going to talk about organorhenium oxides. These are mainly sigma alkyl complexes having main group elements in ligands as ligands along with the sigma alkyls. As discussed in our previous class, this can be rhenium trioxomethyl or rhenium methyl oxo peroxo or trimethyl rhenium oxo. These alkyls are present along with various kinds of oxo trioxo complexes, trioxo ligands attached to rhenium. Now, these compounds sort of gives rise to a special kind of compounds, particularly the one discussed over here. These are called MTO or methyl trioxo rhenium. These MTOs are versatile compounds that are stable in water and also acts as a catalyst for various important oxidation reactions. So, MTOs are versatile, hard Lewis acids, as the metal is in very high oxidation states, water soluble. This is also kind of interesting that organometallic compound where there is a rhenium methyl group, still the compound is soluble in water and can act as both stoichiometric as well as catalytic reagents in important reactions like olefin oxidation, Baeyer-Villiger oxidation, olefin metathesis, olefination of aldehydes, So, what we see that methyl rhenium trioxides compounds of this formula are very important reagents. These are sigma alkyl transition metal complexes, they are hard Lewis acids because of high oxygen state of rhenium, and they act as catalytic as well as stoichiometric reagents in oxidation reactions. And another important property of these compounds are that they, being bound to 3 heteroatoms, are also water soluble. This is something which is unthinkable for many organometallic compounds, because we tend to think that organometallic compound will instantly or immediately decompose in water. So, this class of compounds are extremely good catalyst as well as reagent for various oxidation reactions. They are hard Lewis acids. A very nice application of transition metal sigma alkyl complexes is in form of these compounds. Let us take a look at how these MTOs are synthesized, usually by 2 methods. The first one being with dialkyl zinc. Zinc being the alkyl transfer reagent, at low temperature giving similarly. The other method involved treating of rhenium oxide with ClSiMe3 in THF, eliminating giving the chlororhenium trioxide, which when alkylated with tri-N-butyl tin methyl give this methyl rhenium trioxide. So, these two methods are very useful methods for preparing these compounds. Now, having seen the application of transition metal sigma alkyl complexes, we are going to take up another very interesting topic in terms of application of this complex, which is the CH activation. CH activation is a topic of contemporary research and is a very challenging area, and it is challenging because one CH bond is very high. That means that CH bond is very strong bonds and difficult to cleave. Second thing, CH bond is so ubiquitous that selectivity becomes an issue. So, that is why CH activation is a problem which is yet to be solved fully. Now, CH activation offers certain advantages, and that has been achieved by binding of transition metal to the CH bonds, leading to functionalization. So, the activation of unreactive CH bonds by binding to transition metals can be used for functionalization and that means utilization of fossil hydrocarbons. So, this aspect has tremendous commercial value. And hence, CH activation is a topic which is of contemporary interest. Let me illustrate the various possibilities, exciting possibilities that CH activation can give. For example, it can convert CH4 and carbon dioxide to give acetic acid, which is an attractive target. So, methane being inert is difficult to functionalize, and carbon dioxide is produced a lot in the industry. So, this can give rise to utilization of CH4 and CO2 to produce something useful in the form of acetic acid, and that can be used for making many other value added chemicals. Similarly, one can obtain another important compound, for example, from CH4 to produce methanol. So, all of these have tremendous commercial interest in terms of, let us say, production of methanol from methane or acetic acid from methane, and are being actively pursued in industry and academia alike. And for this reaction, CH functionalization provides attractive solution to this very challenging problem. And in this context, it can be stated that intermolecular CH functionalization is even more is very challenging and difficult as compared to the entire intramolecular CH functionalization. Now, with this background in mind, we are going to look at CH functionalization both at the intramolecular as well as intermolecular levels, and study some of the examples related to it in order to get appreciation of how difficult this particular area is. At the outset, one must say that CH activation to transition metal is thermodynamically unfavorable as compared to hydrogen-hydrogen addition to a weaker metal carbon bond. HH bond to, and this can be illustrated, for example, if there is Lm and it activates dihydrogen, then one forms dihydride. The enthalpy is negative for such reaction, stating that this is enthalpically favored, whereas the same reaction for a CH bond leading to metal alkyl hydride has delta H greater than 0 or delta H equal to 0, and that means that this addition is less favorable and HH addition is more favorable. And the primary reason for this H addition being less favorable is that MC bond is a weak bond, and hence not much of enthalpic gain is realized when a metal carbon bond is formed as opposed to a metal hydride bond. So, metal carbon bond is a weak bond that sort of cannot compensate for the strong bond that is broken when a metal hydrogen bond is cleaved. So, this CH bond, which is very strong, is broken and a weak MH bond is formed. As a result, the delta H is usually positive or at the best thermodynamic neutral, and hence this indicates that this CH addition to transition metal is thermodynamically unfavorable. There are few sigma alkyl transition metal hydrido complex which undergo spontaneous alkane elimination. That means that this alkyl hydride complex is so unstable that they eliminate to give back an alkane. For example, this bis cyclohexyl phosphine nickel hydride alkyl complex spontaneously undergo alkane elimination. Meaning that this complex is very unstable. In the hindsight, the metal carbon bond in metal methyl moieties are generally 40 to 60 kilojoule per mole weaker than metal hydrogen bonds. Now, of the CH activation, which itself is very challenging because of extremely weak metal carbon bonds which are formed, and because of the fact that extremely strong metal hydrogen bonds are broken, let us take a look at different types of CH activation that may possibly occur. It can be intramolecular, as well as it can be intermolecular. Of these, the intermolecular CH activation are more difficult as compared to the intramolecular one. And in this discussion, we are going to take up in more details each of these type of CH activation processes. To begin with, let us talk about intramolecular CH activation. This mainly is observed in oxidative addition of CH bond of an aromatic ring to transition metal. An example is given over here. So, iridium 1 complex chlorine and 3 phosphane iridium undergoes intramolecular CH activation to give the following iridium 3 complex. So, since the CH here, the oxidation state of iridium has changed from iridium 1 to iridium 3, because it underwent the oxidative addition, and also one of the phenyl rings of this PPH3 moiety got activated. So, this hydrogen and this carbon, this CH bond is sort of got activated. The coordination number increased from 4 over here to coordination has number increased to 6 over there, and since the CH bond which got activated is ortho to the phosphine, these kind of reactions are called orthometallation. Or cyclometallation. So, with this I would like to summarize the point that we have discussed in this today's lecture. We have looked into applications of various sigma alkyl complexes. To start with, we looked into organorhenium trioxide type complexes. We have looked into how these complexes were synthesized, and also the various kind of applications of these rhenium alkyl trioxo complexes. Following that, we looked into the CH activation processes which can result in CH functionalization, which is a very challenging area, and then we have looked into various kinds of CH activation processes that are involved. To start with, we looked into intramolecular CH activation, particularly that of cyclometallation or orthometallation that is shown over here. With this, we come to the end of today's lecture, and we are going to take up this interesting topic of CH activation in bit more detail in next lecture, and look into various possible reactions and discoveries made in this area of CH activations, which is of tremendous industrial as well as academic interest. With that, I thank you for being with me in this lecture, and I look forward to being with you in next lecture discussing various nitty-gritty details of these interesting CH activation reactions of transition metal sigma alkyl complexes. Thank you.